Nature occasionally produces physical events so extreme they sound like early drafts of a Hollywood disaster script. Wildfires that spawn actual tornadoes, solid ice crawling onto the shore, volcanoes manufacturing their own lightning storms, deserts that sing, and frozen tundra that violently explodes. We navigate the world assuming a basic set of local rules. Fire travels along the ground. Ice stays locked in water. Sand dunes are silent. But when the physical forces of our planet collide under extreme localized conditions, those rules distort. The boundaries between elements break down, producing anomalies that are terrifyingly real. Looking at the aftermath of a typical wildfire, you see a path of destruction left by a chaotic wall of flame moving across the landscape. In July 2018, the Carr Fire in Northern California encountered anomalously low fuel moisture, intense heat, and a pre-existing zone of cyclonic wind shear. Driven by these conditions, the fire stopped behaving like a localized ground event and initiated its own weather system. Extreme surface heat drove a massive plume of smoke and moisture upward, growing 12 kilometers into the atmosphere in just 15 minutes. It formed an ice-topped pyrocumulonimbus cloud. As that towering cloud developed, it stretched the underlying column of rising air. In fluid dynamics, vertical stretching pulls any existing rotation into a tighter radius, rapidly accelerating the wind speed. This concentrated the surface rotation into an EF3 vortex, packing winds of 143 miles per hour. Unlike a common small-scale fire whirl, a true pyrotornado requires this rare connection to a high-altitude cloud. The result is a vortex capable of wrapping steel pipes around power poles and leveling entire city blocks. In winter, a frozen shoreline is generally a static, dormant boundary between land and water. When massive walls of fragmented ice suddenly breach that boundary and bulldoze inland, people often label them ice tsunamis. But the phenomenon has zero connection to seismic activity or tidal forces. The true engine behind this event is wind. Over expansive bodies of water, like the Alaskan Chukchi Coast, strong, sustained weather fronts transfer massive amounts of kinetic energy across miles of offshore pack ice. This sustained stress funnels that immense directional pressure towards the shore. As the warming, consolidated ice sheets are pushed against the shallow coastal boundary, they fracture, riding up over themselves to build jagged ridges up to 5 meters high. These ice shoves are pure kinetic energy transfers. Through sheer friction and accumulated weight, a continuous push of wind effortlessly drives a frozen ocean onto dry land. We classify volcanoes strictly as geological hazards, ruptures in the crust that expel magma and ash from deep underground. In January 2022, the Hunga Tonga submarine volcano erupted in the southern Pacific Ocean. Rather than erupting in open air, highly energetic magma blasted directly through the shallow sea. This violently vaporized the seawater, carrying it miles into the upper atmosphere. Up there, volcanic ash collided with supercooled water droplets and hailstones, generating massive static charges. Looking at this satellite view of the resulting ash plume, you can see the scale of the anomaly. The eruption produced nearly 200,000 lightning flashes, peaking at over 2,600 a minute, and emitted concentric rings of lightning 250 kilometers wide. By violently injecting ocean water into the stratosphere, a geological expulsion manufactured the most intense atmospheric electrical storm in recorded history. A remote desert dune is typically viewed as a silent, desolate landscape. Yet for centuries, travelers like Marco Polo and Charles Darwin documented deep, sustained booming sounds emanating from the sand. For decades, the leading theory was that this low droning sound was simply a byproduct of the average size of the sand grains scraping together. Field measurements revealed a different mechanical reality. When dry, loose sand avalanches down a steep slip face, it travels over a much denser subsurface layer of sand, creating a distinct boundary between two materials with different wave velocities. As the avalanche generates sound, the acoustic waves reflect off that hard subsurface boundary and constructively interfere. They amplify one another, effectively turning the entire geological structure into a resonating acoustic waveguide. This requires precise conditions, the right moisture level, the exact angle of repose,
and the proper subsurface layering must align to turn a collapsing hill of sand into a deafening, low-frequency acoustic instrument. The Arctic tundra is defined by its permafrost, a thick subsurface layer of soil that is supposed to remain permanently frozen and solid. But across northern regions, scientists are finding massive, shear-walled craters appearing overnight, where the solid ground has violently blown out from underneath without warning. Researchers are actively investigating the precise mechanics, but the primary driver involves immense trapped gas pressure. As permafrost thaws, decomposing organic matter releases methane gas, which builds up beneath the remaining frozen surface until the structural limits of the Earth are exceeded. As the Earth's systems shift, even regions defined by absolute frozen stability can violently burst, leaving massive craters as physical scars of unseen pressure. Our understanding of nature relies on isolated categories: geology, meteorology, fluid dynamics. But when extreme variables align, whether it's high-altitude wind shear intersecting a wildfire or magma colliding with the shallow ocean, those categories overlap to produce phenomena that defy our baseline expectations. Mapping these anomalies proves that nature's most terrifying events follow a strict mathematical logic, occurring precisely where our physical laws reach their absolute limits.